Okay. So what? Okay. What page will we on? Can you go to page 10? So this is next. Oops. There we go. I think this would be great if I could show you with a video. What? This isn't a video. Oh, there we go. Are you playing? We are. Can you see that okay? Can you see that? Yeah? So what they have here is they have a string against the wall and there's a little hammer going up and down and it's shaking the string and it looks like it's making a wave. Can you see that?
Yes.
So it looks like the wave's kind of not moving, but of course you can see it's moving, it's vibrating up and down. The only thing that's happening is the wave is not moving out the room, it's standing in one spot, just moving up and down. So this is a standing wave, or a stationary wave. It's a wave that does not move anywhere, but you can still see it's a wave. It has a wavelength, it has a maximum, it has a minimum, it has a period. So these are standing waves. And I'm not really into well, actually, not really, I suppose. But if I just pause it here, actually, if I go back, let's see. Pause it there. I want you to look closely at the point in the middle. The point in the middle doesn't really look like it's moving. It's staying in one spot. Now I want you to look at the maximum and the minimum. What are they doing? They're moving up and down a lot, aren't they? These are two important points on this wave. The point in the middle that doesn't move has a name, and the point where they move the most has a name. Does anyone know this name? Yeah, what is it? Node and anti-node. So I'll draw that on the board now. But those, I think with a video it really helps you to see it, okay? So these are called standing waves. And the new word you have for this lesson is node and anti-node for those two places. Here in the center and then here at the top. So this one in the middle here is node. I think it's node. Let me just double check that one. It's node, yeah. And then this one here is anti-node. Okay? So can you write that down, and I'll write it up on the board as well. Node and anti-node. So this here is called, what do I say, anti-node. And then this one here is node. And then this one here is anti-node. This one here, node. This one here, node. Okay. I wonder if they can make more, actually. Let me see. I think at the end now look at that. So now, see, this one's different. You see now it has 3 loops. You see that? So in my last one, there was just one, or there were 2 antinodes and 1 node in the middle. Now how many nodes has this got?
2.
It's got 2, 1 there and 1 there. And of course the pieces at the end. But 2 nodes in the middle instead of 1. Okay? So what's really important for standing waves is how many nodes it has. That's what's unique or interesting about them. We should play that for you. See that? So this one now has 2 nodes. He's changing the speed here. So I don't know if he's trying to yes, can you see that now? 1, 2, 3 nodes there. Yeah, there you go. 1, 2, 3. Yeah. Okay. And I think at the end it goes in slow motion, which is kind of cool. Maybe. No. There, that's nice. Okay, 3 nodes. Okay. I suppose, how is this wave different from the waves we were doing yesterday? So, who can tell me what the main difference is here? They're not moving, which means
no transfer of energy.
There we go. No transfer of energy. So the energy is not moving anywhere. So please make note of that as like the definition. No transfer of energy. And what type is this? Is it longitudinal or transverse? Transverse. Okay. In this picture here, it's transverse.
The stationary waves has no transfer of energy.
Yeah, that's a key feature about them. Okay.
So all of the stationary waves are transferred?
No, I don't believe so. I've never actually seen one that isn't, because it's easier to see it when it is. But I would not like to say that they're all transverse. Just all the ones we work with are.
What about waves in sea? Is it there?
No, their waves are definitely moving. It's not standing wave.
So the waves are like straight, they're going longitudinal.
This, like this one here in the picture, is longitudinal.
You just said it was transverse.
Sorry. It's transverse. The ones going up and down.
No, the ones going up and down.
Oh, I'm so sick. I gave it to you, the definition. Just look back the notes and last about. Huh?
Longitudinal is the one which goes up.
Longitudinal is this one, yes. And then transverse is.
Yeah.
No.
Yes.
Transverse.
Transverse is this one. No, just look at your notes from yesterday. What do you mean you don't have them? Did you write them down? So which one did I draw for longitudinal? Say again? This is transverse.
Yeah.
Transverse, longitudinal. Okay. So to answer your question, the most we deal with for standing waves is transverse one. But I'm not going to say that there's not any longitudinal ones. It's just I can't think of any right now. Anyways, for the exam, which is most important, it's transverse. Okay, let's have a look at some examples then with this. Okay, well, actually, just before we go on to that, there is a way to actually change longitudinal into longitudinal into transverse wave. There is a way to convert between them, okay? And this method is called, well, before I say it, does anyone know it? Yes? What is it, Uri? Polarization. So you can make a longitudinal wave into a transverse wave by using something called polarization. I'll try and draw it here. It's not too difficult. So here is our longitudinal wave. It's very difficult for me to draw, but it's coming in like this. Okay? Then it hits this basically like glass, but there's lots of little slits in the glass. Lots and lots and lots and lots. And the result is that when it goes through the glass, only the pieces that are moving up and down are allowed to go through. Any part that's moving left and right doesn't pass through. So in other words, it's like a filter. So when you have your longitudinal wave moving in, and it hits this filter, what happens is, can you look? Like, I mean, if you look at my hand gestures. What's wrong? The glass? Yeah, it has lots of slits in it. And look carefully at my hand gestures, okay? The transverse wave is moving like this. Okay? Now, if you look at my hands, you can see that part of my hands are moving horizontally. If you look at like my fingers here and here, there's parts of it moving like this. Do you see that? And then of course there'll be parts moving up and down like this. It's hard because I can't make my hands bigger. Okay, but you think of it as expanding out. When it hits this filter, all the movement that was horizontal like this, it cannot pass through. But all the movement that was vertical is allowed to go through. So the result is, for the wave, it cancels or destroys all the horizontal and leaves me with only the vertical movement. So it takes the wave longitudinal like this, it passes through, it cuts out the horizontal and leaves me just with vertical going up and down. This is called polarization. Can you go backwards? Can you go from transverse to longitudinal? What do you think? You can't really, because this works because it destroys part of the wave. So you can't really go backwards through it. It's a one-way process. That's what polarization is. So I mean, there's nothing to calculate here. It's just you need to know what the word is. So can you write down your definition or explanation of this process, okay? So what might be keywords we need here? Destroys what? The horizontal motion of the longitudinal wave, leaving only vertical motion, i.e. a transverse wave. You don't need it exactly like that, but I'd like you to write something down, please. Tal, did you watch that electricity video? Not yet. You know what I'm talking about, don't you?
The one that we're trying to solve in the end of the in the
There's two mistakes in the market scheme.
Is it the very last video on electricity? It should be, right?
It's on the bottom of the Moodle page. Okay. Do you have that taken down? Yeah? Okay. Okay. So, if you want, you need to go to page 22, because in fact, the first section of this Waves book, all I really wanted to do in it was introduce kind of basic terms and ideas. So you'll notice if you go to page 22, it continues with stationary waves. But an important stationary wave, a sound wave. Okay.
Page 22.
22. Okay. Right. I'll just draw this here for you. So what you need to picture here, for example, is like a cup. Now, or a glass tube or something like this, okay? Pipe, yeah. And there's a sound wave that goes inside of it. Now if the sound wave is like this, it'll go inside, it'll hit it, and then it'll come back out, you know. But if you have the right wavelength, what you can do is, when you make the sound here, if the wavelength is the same length as the tube, then you make a standing wave. So it'll make a standing wave. Okay, so that's actually a very, very useful result. And I'm going to show you a couple of different possibilities. So the first one is it makes a standing wave, well, like what I just drew. The second one is it makes a standing wave like this. So this is if we have lambda inside of it. This one here would be lambda over 2, and then this one here, I can't quite see it, but what I'm doing is I'm going from the min to the max, so it's lambda over 4. So there's a standing sound wave inside the glass, and what's going to happen is the glass will shake a little bit, because if you picture it, if you have a wave inside of it and you're shaking it, then the boundary is going to shake as well. So my question to you is, of those 3 standing waves I've drawn, which standing wave would make it shake the most?
The first one.
The last one.
First, middle, or last? We say last?
First.
Say first?
Last one.
Last one?
I'm going to say the middle.
Why not? Now, it's not the first or the second, it is the last. But the reason why?
Because it has the highest amplitude.
Not this, no, yes?
In the first one, when it hits up, it's also
Exactly right.
It gets a shot.
Exactly.
The last one is
Yes. If you look at the first one, every time the standing wave moves up, there's another half that moves down. So in effect, it doesn't really shake much, because you have a force up and down and they cancel. If you look at the second one, you have a force that goes up and then down, and then up and then down. But that's the same as the last one, isn't it? A force that goes up and down, up and down. So why is the last one makes it shake more than the second one? Yes? Yeah, not quite. I'm just talking about this picture for the
It
moment.
has a bigger wavelength.
It has no, and it doesn't have a lot of anti-nodes.
No?
The time though.
No, I'll tell you. When I have my tube here, there's forces going up and down. But of course there's also wanting to turn. Now if you look here in this one, the middle one, if I call this force here F, it's still F in the last diagram as well. But there's a big difference in the last one. The F is further away from the end of the tube. So that makes, do you know Tom? What?
Is it connected to the turning?
Turning force, yeah, what happens?
The G is bigger.
Yeah, the distance is bigger, so the turning force is bigger. So in other words, of the 3 possibilities, the last one is the one that will cause the vibration of the glass. That's important, because that means that the length of the glass is 1/4 the wavelength. So if you take the length of the glass and multiply it by 4, what do you have? The wavelength. So this is how you can find the wavelength of sound. You need to figure out how to make your pipe shape. Then whatever the length of the pipe is, you multiply it by 4, you've got the wavelength of the sound. That 4 is not something in the formula book. Just like with the time constant question, it's a number you need to remember. So the result we have here is, for maximum vibration, we should use 1/4 the wavelength. Okay, did you write that down? You got that?
So could you just draw another one? How does the opposite of the, I mean the opposite of the wave?
Huh? What do you mean?
Sound wave travels in,
Yeah.
and there's it reflects this way.
Yeah, but what happens is it reflects in such a way as to cause a standing wave. So picture this just like the video I showed you, except instead of a rope, it's just a sound wave. But if it helps you, just picture that as a rope,
Right.
shaking inside the tube. Yeah, like that. Yeah. So what do you need for the exam here? Let me give you what you could get in the exam. Can I scroll down? So in the exam, I'll draw the picture. I'm sure people know this item. Do you know a tuning fork?
Yeah.
You take it, you hit the table, and it makes a sound. The great thing about tuning forks is that you know the frequency of the sound wave it makes because it says the frequency on the fork. So, I'm just going to make up numbers here, okay? So let's just say the frequency, I don't know, is 500 hertz. So when I hit the fork here and it makes the sound wave, the frequency is 500. Okay? Now, what I'm going to do is, I'm going to put this beside its glass tube, and I'm going to say it's 0.2 meters long, and the sound goes in. I won't draw it actually, I'll let you draw it. So my question is this: if the tuning fork makes the pipe shake, resonates, shakes, what is the speed of the wave? So let's write down the formulas we need. We have the first formula that this length here, what does that equal for the wavelength? It's the wavelength over 4. And we have another formula, in fact I think it's the only formula I gave you yesterday. Yeah, V equals F lambda. So I want you to tell me the V. Can you do that now for me please? What's the V? Now, by the way, I just made up the numbers, so the V could be something silly, but let's see, what did you get? Hey, that's not too bad, actually. The speed of sound is about 330 meters per second.
400.
Oh, yeah, no, I'm saying the true speed of sound is 330. So in my example I made up, it wasn't too far off. So we got 400. Is that difficult to do? No. And that was a section A question, I think maybe 2 years ago. So you can see, you sometimes get very nice questions like that. What's difficult about this question though is that formula is in the book, but this formula is not. And this is why some students couldn't do it, because they didn't know this fact. The fact that if the pipe is shaken, it's because there's a 1/4 wavelength standing wave inside of it. So again, I'm saying this so you can really make it clear in your notebook, not in the formula book. You need to know that. Okay. Oh dear. Let's see. Okay, I'm trying to find if I can find a pipe one here for you. Yeah, like I mean, there's another formula or fact I have to tell you now, but it means we can do one of the questions here. Okay. We know sound is a wave. What else do we know is a wave? Light is a wave. But there's other things like light as well. Yeah, radio wave, gamma wave, there's lots of waves, okay? Radio wave, TV wave, magnetic wave, there's loads. What all these types of waves have in common is they all have the same speed.
At the same time, so microwaves as well.
Huh? Microwaves, yeah. Microwaves, they all have the speed of C. In the exam, they'll sometimes say a radio wave, and they don't tell you its speed. That's okay. You know that its speed is C.
Which is speed of light.
Yeah, speed of light. The question I was looking at, which I'd like you to do now, it's just a small part of the question, is they give you the frequency, 2.4 gigahertz, and they want the wavelength. So I'd like you to do that for me, please.
The wavelength is 3 times 10 to the power 6.
10 to the 8, I thought.
3 times 10 to the power
6.
10 to the 9. Are you sure? So it has to be 8.
I think it's 8. No, the 8 is 300 million. So it's 8.
No, sorry. He's talking about the speed of light, not the giga. Yeah,
It's 8.
that's okay. It's 10 to the 8, isn't it?
Yeah, it's 8. It's 8.
Yeah. So the C is 3 times 10 to the 8, and giga. Yes, what's giga? 9. Because mega is 6. Yeah. Am I sure about giga or what?
Speed of light.
Yeah, 3 times 10 to the 8.
I was looking thinking you want to make sure just Google it.
Well, I actually have it right here as in the formula book. Speed of light 3 times 10 to the 8. Case closed. Right, did we get an answer?
Yeah. 0.125.
0.125 is the wavelength.
Yeah.
So 12.5 centimeters. How many marks for that do you think?
1.
Better than 1, 2. Not as good as 3. 2 marks. So it's okay, isn't it? That's nice and simple. But as I'm looking here, you don't get many of those. Oh, here's one. Let me ask you. What is meant by a transverse wave? Yeah, what is a transverse wave?
The wave that travels,
Perpendicular.
the wave in which the direction of
Vibration is
perpendicular.
perpendicular.
So it's a transfer.
the direction of the transfer of energy.
Can't you see source of energy?
The problem with the word source of energy, it has no sense of direction, it's just a point. So I need some kind of reference to movement. How many marks for that definition?
1.
2. The diagram. Here's another one. Wait. Same question, okay? So this is section B of the exam. You listening?
Yep. Yeah.
First one you just did for me for 2 marks. Next part for 3 marks. What is meant by standing wave and antinode? So standing wave is a wave where no energy is transferred. And it is typically what type of wave? A transverse wave. And antinode? It's the part of the wave that moves the most versus
the maximum and the minimum.
Maximum minimum point. Very good. So how many marks for saying everything we've said so far? 5 marks.
5.
Now the next part is the next part is draw a standing wave and label the nodes and antinodes.
Draw a standing wave. That's easy.
2 marks for that.
Then easy.
And then the last part here is calculate the wavelength if the frequency is 285. You actually just did an example like that.
Yeah.
So this question here is about a radio wave. So give me the answer, please. If the frequency is 285 megahertz,
So that's 10 to the 6.
yeah, what is the wavelength?
1.05.
1.05, yeah.
Now that's the wavelength.
Yeah.
Now for the question actually said, and just think before you say, what is the distance between the antinodes? So just picture the wave. How far apart are the antinodes? Half the wavelength. So divide that by 2. Tell me what you get.
So 0.5.
Yeah, so in this question here, the antinodes are 0.53 meters apart. So, how many marks for what we could basically do speaking, not writing? 2, 3, 2, 2. 2, 3. So 6, 7, 8, 9, 10 marks.
Okay.
Not bad at all, okay? So it's nice for the exam. Now this is section B. The other 10 marks we can't do yet. But already we can do half of this year. That, if you're wondering, that was 2006 paper. No, you could get that one. You could. That was 2006, section B. If you want to have a look at it tonight, if you're curious, it's B4, 2006. If you want to read it, okay? It's on Moodle. Yeah? Yeah, 2006. Okay. Can you look please at the diagrams? Please. You can tell I'm very sick this week. Cooperate with me. Can you look at page 24 and 5, please? Now, do you see at 25, the top right? Do you see the diagram there? The top right on page 25. That's the diagram I just drew that says a quarter of the wavelength fits inside when it vibrates. Okay. Now, if you look at the bottom of the page, they just give different examples of standing waves. But what you notice here is, do you see in picture A, B, and C? You see those 3 there? How many nodes are in the first one? In the second one? And the last one? 3. Now do you notice in the description it says first harmonic, second harmonic, third harmonic. You see those words there? Harmonic just means how many nodes. So I need you to make note of that word. And by the way, you don't count the nodes at the start and at the end, just the nodes that are in the middle. So what does harmonic mean? Number of nodes, not counting the boundaries, just in the middle. Huh? No, just number of nodes.
So in this case, the word N is node.
In the diagram, N stands for node, and is there an A as well?
Yeah.
For antinodes then.
So it can't be 2 nodes there.
I think it's complicated if you start referencing antinodes. It's enough just to say it's the number of nodes between the endpoints, but not including the endpoints. Okay, because if you think about it, you always have the node here and the node here.
Yeah.
So don't count those, just the ones in the middle. Okay, did you write that down? Harmonic equals no, but don't give me a full sentence. Oh, there we go.
Yeah.
Sorry, I was reading this one here.
No, that's
It's just, yeah, okay, that's fine. There we go, actually go to page 26, please. So, again, just more examples of standing waves. See here at the bottom? More examples of standing waves. But they give you an example of why this is important too. You see this big picture here? Do you see that picture? It's of a musical instrument called an organ. Yes, what some people don't know this word. This is called an organ. Organ pipes, yeah. Now, what you maybe can't see in the diagram is there's lots and lots and lots of pipes here. You see that? Yeah. Lots and lots of pipes. And the reason for the different sound from the different pipes is because they're different lengths. And different lengths means different number of nodes and antinodes. In other words, different vibrations, so different sounds, okay? And different overtones and things like this. Oops.
Oh, we've seen this one already.
Sorry to disappoint you, so. Now, if you look at this chapter, there is lots of formulas. Formulas you don't need for the exam, which is good for this chapter, okay? What you need for the exam is actually only for this chapter is only that one formula I said about the pipe. Well, that one was from yesterday, yeah. So for today, the only new formula is the one about the pipe.
The length is
1/4 of it. Oh, great. And then on page 29, again, you can see the tuning fork. You see it there?
Yep.
And how much of the wave do they have? 1/4. Now, you might say, why does the wave not go to the bottom? And that's because it's full of water. So in other words, when you put water inside it, all you're doing is changing the length. Huh? Okay. Focus, people, focus.
it's the what?
Yeah, so we have our pipe, made of glass. Can you change the height of a glass pipe? Of course not. So the way you change the height is you fill it with water. So when you fill it with water, what you're doing is you're making it shorter. So you have your tuning fork, hit the tuning fork, hit it against the pipe. Do you hear anything? No. And then you fill it with water. And what you're trying to do is to find the height. Once you find it, then you know that this here is what? 1/4 the wavelength for the sound. So the putting the water in it is just a way of changing the length of the pipe. That's all. Could be one we actually do, but I don't have any tuning forks, so I'd have to buy some. I actually don't think tuning forks should be expensive, but I don't know.
I can buy one.
You have them without asking.
Yeah, but were you at an actual university lab? Yeah.
Okay, if I...
This ain't no university.
In which range of the prices can you buy for?
I'd probably be allowed to order something up to maybe €20. So if you can find a set of tuning forks for €20, send me the link.
I can buy it, give it to you, and you'll give me the bill. I'll give you the bill.
Yeah, but the thing is, the school would need to order it so that I'm not paying for it. You know, if you find a link, if you actually, because we don't need much to do. We just need a tube and some water. So I think that is easily found.
I think it's easier to buy it normally in the shop.
I think so too. Actually, a music shop might have it.
Yeah, that's what I meant.
Yeah, so it should be easy to find, yeah. Okay, let's have a look here now. I'd like you to look at page 35 for the questions. So can you mark these questions for me, please, before I die? Number one, I'd like you to do A and E, the two calculations in number one. In number two, again, I would like you to only do the calculation, which is A. I think in number four there's a calculation as well.
You have to do number 4?
Yeah, the calculation is, yes. Number four, you can try, please. Well, yes, the second part only. Yeah, because they give you the length and they give you the speed, and I think they want the frequency. And so you can try it, I think. Oh yeah, and we can definitely do number 5 as well. Hang on. Let me look at 6. They give you the length and they give you the frequency. So they give you the wavelength and the frequency. So I think you could.
We need to
Oh, number 6 isn't, I think, a calculation.
Yeah,
It's just
where
true
each
false.
follow instead.
Nah, forget about 6.
I do think it might be enough.
Oh, please. Number 10A is easy. They give you they give you the wavelength and they want the distance between the nodes. Okay, I think that's enough then.
Start it here and finish it home.
I think there's 5 minutes left, and in fact, probably get them finished in 5 minutes. So, I think you could do those in 5 minutes, couldn't you? I mean, they're, as you can see, they're so short you don't even need to write anything in some case.
Can we write that just this?
If you can fit it in the book, that's fine. You can write it in the book, I don't mind. I mean, for this topic, it's short.